Recent advances in manufacturing have spurred exciting research in fabrication-oriented design. However, most of the previous work assumes that a design completely determines a fabrication process. In a typical application, however, multiple fabrication plans can be used to generate one single design. Imagine you want to fabricate this birdhouse. There are many choices of possible cutting tools, usage of material stock, and order of operation. Such optimization of the fabrication plan is important to minimize the fabrication costs. But it naturally depends on the finished design. However, when creating and optimizing the design for its physical behavior, it is essential to understand the fabrication process as it defines what can be physically realized. This coupling between design and fabrication makes optimization challenging. Our key insight is that both design and fabrication plans are programs. A design can be expressed as a sequence of geometric construction operations, and a fabrication plan is a sequence of physical instructions. This can help us solve problems in design for fabrication by drawing ideas from computer systems. One of the most influential developments in computer architecture was the introduction of ISAs, which serve as an interface between hardware and software and enabled independent development of both sides. In this work, we ask if something similar can be done for design and fabrication. We address this question in the carpentry domain. We present HELM, Hardware Extensible Languages for Manufacturing. Our system includes a high-level language for design and a low-level language to describe fabrication instructions. We also designed a compiler that maps the design to a fabrication plan. Our high-level HELM is inspired by traditional CAD languages but focuses on subtractive operations. For example, we can take a box and cut along a curve. Our low-level language is process-specific. For example, take a 2x4, set up a chop saw at a 30-degree angle, and cut. Since the language must take into account individual fabrication processes, our architecture has been designed to be extensible so that we can easily add new fabrication hardware. Our compiler maps the design to a fabrication plan, and it is responsible for design validation and optimization. Such optimization is challenging, first because a fabrication plan involves a long sequence of interdependent steps, choosing the material stock, packing the parts on the stock, and then defining the tools for each cut and choosing the order of the cuts. The second challenge is that there are multiple conflicting objectives. There are two possible fabrication plans for this bookcase. The first one uses less material than the second, but the second can be executed in less time as the layout of the parts allows for part stacking or use of smaller number of machine setups. We solve these challenges by combining eGraphs data structures from programming languages literature and combining it with genetic methods for multi-objective optimization. Here's an end-to-end example. Before starting their design, users need to define different carpentry tools and materials that are available. The user can then create a design by interacting with an IDE that automatically generates high-level HELM code. The verifier lets users intuitively explore the design space while validating that every design is fabricable. After the design is complete, the compiler generates a set of solutions for fabrication plans that correspond to different fabrication cost trade-offs. The user can then select one and follow it to make the carpentered item. A user interface guides the carpenter in following these instructions. Please see our paper for further details and results.